This is Amanda Welch welcoming you to this Bite Size Bio web seminar, which today is sponsored by ZEISS. Since 1846, it is the mission of ZEISS to constantly improve microscopy through innovation. With our unique portfolio of light, electron, ion, and X-ray microscopes, we enable research and industry for the challenges of tomorrow. Highly skilled application specialists support your work and make sure you get the most out of your investment. Today's presentation is titled, The Fast Module for ZEISS LSM 880 with Airyscan, confocal super-resolution imaging with 4 times the speed and improved signal-to-noise ratio, and is being presented by Chris Power, a 3D imaging specialist from ZEISS Microscopy. Chris studied biology and oceanography at the University of Southampton and became a product manager for confocal systems at Bio-Rad from 2000 to 2004. Afterwards, he moved to Germany to develop confocal and light sheet technologies at ZEISS, including a project leader position for LSM 700 and the LSM 800. In 2011, he moved back to the UK and became a 3D imaging specialist. As always, we will have a question and answer session after the presentation. So please type any questions that you have into the questions box, which appears on the right-hand side of your screen. I'll put them to Chris at the end. So now, over to you, Chris, for the presentation.
Good afternoon. This afternoon, I want to run through the ZEISS LSM 880, in particular the Airyscan module, where we've introduced a new function called FAST. Confocal technology, as many of you know, has been around since 1984, and in the following 32 years the technology has evolved dramatically. LSM, or laser scanning microscope systems, have evolved from very simple point scanners to 3D imaging, to fluorescence, to 4D imaging with time-lapse, and even to more complex techniques where we analyze the underlying spectra or the molecular movements, so on, within the sample. And confocal microscopes have therefore become a very versatile and flexible form of microscopy. Over time, in order to improve the image quality within the systems, we introduced something called the Airyscan. So the Airyscan was technology that's available on the 800 and 880 platform. It was introduced at the end of 2014, and it dramatically increases the signal to noise and the resolution that is possible to get using point scanning technology. So on the left here we see an image taken with confocal, applying the parameters to get the best we can out of the image, and on the right we see both the signal to noise and the resolution increase that Airyscan gives you. What I would like to introduce today is the additional change that you can get with the FAST module. So what we have here is a 40 micron deep Z stack in zebrafish brain, and we're looking at a 14 micron cutout of that. On the left we have a gallium arsenide phosphide detector image that was taken in 24 minutes. On the right we see the same stack taken, in this case with the Airyscan detector, in a quarter of the time, and with improved signal to noise and with improved sensitivity. This is what the FAST module gives you. And not just using this in order to increase acquisition time, this can be used for live cell imaging. Here I show an example of cardiomyocyte cells which exhibit buckling, so they're moving backwards and forwards, and at the top there is an example of an image taken with a resonance scanning system of these microtubules, and on the bottom using Airyscan in the new FAST mode. So that's what I'd like to show to you today, the signal to noise and resolution improvements we can get, not just on fixed samples but on live samples at speed. So if I come back a little bit towards the motivations towards developing this technology, it's always been known that putting light into your sample can be damaging. The more light you put in, the more you risk introducing toxicity, bleaching, and destroying your sample and image quality over time. This has been well known, and effects such as bleaching are also quite dramatic and noticeable. Whilst that's been known for many years, there have been publications as recently as last year and this year, where people are now beginning to concentrate on the lesser visible effects. So these are effects that may happen to your cell where it changes its behavior, it changes its viability, it changes how it interacts, all based upon the light exposure you put in. So these are effects that may be more subtle than bleaching. So it's more important than ever to try and put in the least amount of light possible so that you don't introduce physiological changes in just a few frames, as can be the case. Now, because the sensitivity in the system has been a key feature, this has obviously been the drive behind the scan head design in our confocals for years. In the case of the 880, we've made a number of big innovations. We've enabled a system called the quasar detector where we split light and we allow you to acquire light from all different colors of the spectrum simultaneously. We do that by dispersing the light in an effective and accurate way, using a grating and a recycling loop so that we don't waste any light in this process. We use the best quality detectors, such as gallium arsenide phosphide, in order to get the highest quantum efficiency. And we do that using a scan system where we have the highest scan time efficiency available. So we spend as much time as possible scanning the sample as opposed to dead time when you're not imaging. And the reason why you want to do this is really to get away with the lowest power you can. As I already alluded to, you want to put the least amount of power in possible to not kill or introduce toxicity into your sample, and yet you need decent image quality. So in this image here we show actin tubules imaged with very low laser power, so in this case 820 nanowatts. And if you look at the middle of this cell and you look at the dots within the red circle, these are actin attachments. So if I now play a movie of that, what we see here is the top, this is imaged with a conventional PMT, and at the bottom with a gallium arsenide phosphide detector with twice the signal to noise. And here we've boosted the contrast, and you can see the actin microtubules moving clearly at the bottom, but they kind of become buried in the noise in the top movie. So for live dynamics, this is pretty critical. And it's just as true when you're imaging fixed samples. So here, if we take an image using a normal detector and using a gallium arsenide phosphide with a fixed sample, you can see that improved sensitivity will give you a higher contrast relative to the background. So all the time, be it live or fixed, you want the most sensitivity you can get from your sample. Now, when we were developing the 880, we went out and spoke to many customers about what they wanted to see, and obviously we got many different answers, but the majority of them were based around what we call the key cornerstones of confocal, so be it speed, resolution and sensitivity. With the Airyscan in 2014, we really tried to address the lion's share of that, so resolution and sensitivity. And by introducing Airyscan, we've enabled 4 to 8 times better signal to noise, and we allow a resolution improvement of up to 1.7-fold in X, Y and Z. So how do we do that? Well, the innovation came in the form of Airyscan, which is an additional detector which couples onto the side of the 880 or sometimes the 800 scan head. The whole purpose of the Airyscan is to allow simultaneous super resolution imaging at increased sensitivity. So I've already kind of alluded that you don't want to put too much power into your cells, but we haven't got down to resolution yet. This is an image with a group looking at telomere replication. They were looking at fluorescent markers at the end of the chromosomes here, and if I zoom in, here you have an image on the left taken with confocal, where because of insufficient resolution you can't tell whether there's 1 or 2 dots at the end of the mitochondria. If you look at the right hand image taken with Airyscan, you can begin to resolve, and you can count and say, okay, there are 2 red dots here, there are 2 green dots here. But resolution and sensitivity come hand in hand. The improved resolution of the Airyscan is only useful because it also comes with the sensitivity increase necessary to see that. Now this dot example is quite a good one to maybe roll into how the Airyscan works. If you imagine taking an image of some beads, so the image at the bottom shows some 170 nanometer beads, and at the top we see a 1 area unit pinhole. If we close that pinhole down and we move it about, instead of seeing beads as we see here, we would look at the beads and we would see them from slightly different angles. So what this image is showing you here is a cartoonized 3-color pinhole, and it would show you that the bead in the, say, the left-hand side of the image, you can see offset by green, red and blue. So depending on which smaller pinhole you looked from, you would see the bead at slightly different angles. And that's really the key to how we started to design Airyscan. So in the Airyscan, we replace our 1 area unit pinhole with an array of micro pinholes. We have 32 small gallium arsenide detectors, each of which cover typically 0.2 area units. We can change this, but typically 0.2 area units, and we detect all of this simultaneously. So if we now look at that image of beads again, if you imagine looking at those beads and you image not with the central element from the Airyscan, but from the 6 elements around, if you look at what those elements see, they each see the beads but from a slightly different angle. So as we play through here, you see the beads, but your images kind of swirl round and each look at the beads from a different angle. If you average those 6 images, you get the image you see on the right here. If you take the next ring out and play through those, the movement is more severe because they're imaging the beads from a slightly different angle. And therefore, if you then average those images, it's a little bit blurrier because you have a bigger movement. And then finally, the outer ring of the Airyscan, the movement is more pronounced. And so when you average it, you get a blurrier image still. So if I show you each of those elements in turn, we have the image on the left is the central element, and as we go from left to right, we see the images averaged from each of the rings. And you see, obviously, the more off-axis, the blurrier the image becomes. So in normal confocal, when you open the pinhole, effectively you're saying, I want the left image plus the next image plus the next image, etc. And your image does get brighter, but it gets blurrier. Well, because we've acquired each of the images individually on the 32 elements, rather than simply and dumbly adding these together, we can take them and we can shift them and digitally add them and remove the offset in the process. So if we do that, we get the images on the bottom. So you begin to see that the images from the next ring out and the next ring and the last ring do have improved resolution, and they still contain a lot of the signal. So if we then average all of those together, we get improved resolution and signal to noise. So just to show that, here we have the beads again. Here we have an image of the beads with this image shift applied. And then finally, we can apply deconvolution to those images before we merge them in order to improve the resolution further. So throughout this process, we end up going from the confocal image on the left to the Airyscan image on the right. Now, part of the reason for the resolution improvement is because we use a smaller pinhole. There is a graph shown at the top of this slide which shows the relationship between pinhole size and light acquired. You may see slightly different versions of this graph, but effectively as you close the pinhole you begin to reject light. As you close it under 1 area unit you begin to reject light that's even from the plane of focus. The reason you may see slightly different versions of that graph is it depends upon emitters within the sample. So if you have a single molecule in 3D space, so a very physicist's example of how a confocal works, you see something like the blue line. If you have a more dense structure, the relationship is closer to the red line here. And regardless of how dense the structure is, the rule holds that the smaller the pinhole, the less light you have. Well, regardless, even on a non-Airyscan confocal, you can close your pinhole, you can deconvolve the image, and if you've got the signal to noise, you can begin to get images that approach the quality of the Airyscan. So underneath the graph here, we see 3 images. The 2 images on the left are acquired with confocal at 0.6 area units and then are deconvolved, and the right-hand image is acquired with the Airyscan. And what we see is that if we average 4 times, we don't quite get the signal to noise. If we average 8 times, the deconvolved confocal images are beginning to approach the Airyscan image. So if your sample is bright enough and you wish to deconvolve, we offer deconvolution. For a couple of decades now, we've had integrated deconvolution within the ZEISS imaging software. One of the reasons people haven't used it is because it takes a long time. Deconvolution can be quite computationally intensive. Recently, people have started to look at GPUs, so the graphics processing unit within the computer, and realizing that if we run computer calculations through this, we can get a speed increase. So this is the GPU powered processing, and I'm pleased to announce that we're just introducing GPU deconvolution into our integrated deconvolution, and so you can now increase your time, or decrease your time to process images by about a factor of 20. It depends on the image size. Here I show a couple of examples of images from 90 megabytes all the way up to 16 gigabytes, and the processing time in seconds on a CPU or seconds on a GPU. So if you're interested in that, we can offer that for wide field, confocal, any of our 3D microscopes. However, there will be times where you just don't have the signal to noise or the well-resolved PSF in order for deconvolution to be effective. Here is an example of a cricket embryo imaged with Airyscan on the right-hand side and with non-D-scan detectors on the left. And if we take the non-D-scan detector image and we deconvolve it, we do get an improvement in signal to noise and resolution, but it just isn't sufficient. Now you may ask, well, why not just increase the power? Crank the laser power up and get the signal to noise we need. And you can do that. The image I show here has an image taken of cells with 4% power on the left with a closed pinhole and deconvolution, and with 0.5% power with the Airyscan on the right. And you see that you can begin to get comparable signal to noise and resolution. However, if you try and do that over time, you will find that by increasing the power by a factor of 4, it's not surprising you end up bleaching and potentially killing your cells. So if your sample isn't bright enough and you want dynamics, that's what Airyscan will powerfully bring for you. If I show you that in publication form, there was a publication in Science in April this year with a group looking at microtubule buckling. Here they were trying to quantify the change in amplitude in the microtubules between the resting state, where they effectively look like a line, and their buckled state, where they look like this S shape you see at the bottom. And in the case of confocal, it was impossible for you to get sufficient signal to noise in order to image this buckling versus straight state. Whereas with the Airyscan, we were able to get the signal to noise to quantify that. If I show the example of resolution improvement in live cell, here we look at a mitochondrial membrane marker, again with confocal imaging on the top image and with Airyscan on the bottom image. And here you can clearly resolve the membrane markers using Airyscan. In this case, these were images taken every 18 seconds for about 20 minutes. And if you are going to try an image for minutes, hours, long periods of time, you really want to be able to image that with the lowest amount of power possible. Mitosis is a particularly sensitive event to the laser power you put in, and here we show a two-color image taken on Airyscan showing very quick mitosis development. Now, I mentioned the resolution increase that's given to you by Airyscan. Airyscan not only increases the resolution, but it does it quite easily on any dyes, any sample prep that you have fluorescently labeled. This is something that is typically done by super resolution in the form of, say, structured illumination microscopy. This is another technology that also works on any dyes and also gives, in the case of super resolution, about a factor of 2 resolution improvement in X, Y, and Z. However, super resolution microscopy, like other forms of super resolution microscopy, is typically limited to samples of about 10 microns in depth. In this case, we're imaging cilia, and the imaging here is done with a structured illumination system on the left and an Airyscan system on the right. The image itself was actually imaged through the tissue, and so because of the scattering that was induced on the SIM system, you get artifacts, but on the confocal, on the Airyscan system, because it's still based around the confocal premise that there is a pinhole effect, light that doesn't hit the Airyscan detector is rejected much more efficiently than in a structured illumination system. You reject a lot of the scattered light, therefore you get a much more cleaner, much less artifact prone imaging. Not only can you use visible excitation, you can use multiphoton excitation. So because the system deals with scattering on the emission side well, it makes sense to couple it with multiphoton so you can reduce scattering on the excitation side. So in this case, this is Drosophila brain imaged with a large working distance low NA lens. Here we see images on the top taken with 1 photon excitation. Gallium arsenide PMT on the left, Airyscan on the right. And here we see at 300 microns depth, we just don't have the great signal coming out. If we switch to 2 photon excitation, we manage to get the laser power to that 300 microns depth, but we can also get it out, and if we detect that on the Airyscan, we can get better signal to noise and better resolution even than NDD or non-D-scan detection. Now there will be a depth if we pushed even deeper. If we push half a millimeter, even deeper still, there will be a point where non-D-scan detectors begin to take over from Airyscan. So it's not that non-D-scan detectors are completely obsolete. It's just that at the less, at lower depth penetrations, Airyscan will be superior. If I come back to that pie chart of requests that we received when we developed the 880, I covered that Airyscan, as it was introduced in 2014, covered elements of signal to noise and resolution. But in terms of frame rate, it was limited. What we wanted to do was push the frame rate as fast as we could in order to really push the boundaries of live cell imaging. And that's what we've introduced with the introduction of the fast module. This will allow us to use Airyscan but 4 times faster. So simply put, it will allow super resolution with improved sensitivity, but also now with speed. If I show you an image example here we have a reasonably large format image taken on the left using traditional confocal scanning. This is looking at GCamp within zebrafish. And here we see an image taken at about 3 frames per second. We do see calcium responses, but we also don't see those particularly quickly, so when we try and graph that, we don't necessarily have a lot of data points. But we also see movement artifacts. When the zebrafish twitches, we can see the image stripe. On the right hand side, we have the image taken at 4 times the speed, so about 12 frames per second with the fast mode. And here we see not only do we get a much more static image of the fish because of the quicker frame rate, but when we plot that, we get a much smoother curve, and we even begin to get some data points on the rising transit. So, how does it work? Well, we still have the excitation coming in laser form, but we use not just a point illumination but a small line illumination. So when we shine the light into the sample, we illuminate not just one spot but 4 pixels in parallel. When the light returns through the scan head, we direct the light onto the Airyscan, we go through the filter wheel, we zoom the light, and we image the 4 pixels within the sample that we've illuminated simultaneously onto the Airyscan. Because we have this multi-array detector in the Airyscan, we can image these 4 pixels at the same time, and then we can apply the same principle that we did in the Airyscan, in point mode, of shifting and adding together light from the neighboring pixels. And by doing that, we get some of the benefits of Airyscan in terms of increased sensitivity and resolution, but we do it much quicker because we're parallel. In addition, because we spread the light over 4 pixels at the same time, it means we can use lower laser power to do this. Oops. So just to show you again how we illuminate and how we detect, the top illustration shows point illumination used in Airyscan and Confocal, and then how we detect that using the whole array of the Airyscan. At the bottom, when we use Airyscan in fast mode, we illuminate a small line of 4 pixels at the same time, and we detect that using 16 of the elements on the Airyscan. And so what that means here is we scan lines 1, 2, 3 and 4 at the same time, and then lines 5, 6, 7, 8, etc. And by doing that, we can sweep down our image 4 times as quickly. So we can cover 512 by 512 pixels at 19 frames per second. We do it with a resolution increase of about 1.5-fold, and we do it with a signal to noise increase of about 4-fold over a 1 area unit. So if we now show an example of what this looks like on a kind of moderately fast sample, here we have an image of Croto cells with GFP, so live HeLa cells. Here we have an image taken at 1K by 1K pixels. If we zoom in on just a crop on each of these 2 images, these are taken at 7.5 frames a second. So on the left we have an image taken with a resonance scanning system, and on the right we have an image taken with the Airyscan. So you can see with the same pixel count and with the same frame rate, we can get a better signal to noise and really track these finer movements. Looking again at these cardiomyocytes that I showed earlier, with the fast mode of Airyscan, we can really push the speed aspect here. So the movie taken at the bottom was with the fast mode of the Airyscan at 96 frames per second. We've slowed the playback rate to about 10 frames per second, so you can actually see the buckling here. Before the fast mode was available for Airyscan, if you wanted to try and touch these frame rates in a point scanning system, you had to use resonance scanning. And resonance scanning, whilst you can get these kinds of frame rates, you have a very, very short pixel dwell. So you simply reach a point where you can't increase laser power because either you're going to introduce nonlinear bleaching or you will kill your sample. Whereas because of the sensitivity increase and the parallel illumination in fast, you can get these fast frame rates. So now you have that improved signal to noise. You can either use it just to image as fast as possible, or you can choose to do different things. You can choose, for instance, to image larger fields of view, or you can image many colors, or you can just image for much, much longer. To really illustrate the point again and the difference in the fast mode to confocal, here is an image of cardiomyocytes labeled with fluo4. If I play the movie at the top, this is a confocal movie showing calcium, and this image is taken at, or this movie is taken at 15 frames per second with a pixel dwell time of 320 nanoseconds. And we do see some sparks occurring here. We can deduce something from this movie. The image at the bottom is taken at twice the frame rate, so 30 frames per second, but with a much longer dwell time, 580 nanoseconds, than with the fast mode. So because we're parallel, even though we're going quicker, we can actually use a longer pixel dwell time, and that will give us greater sensitivity. To kind of show what that looks like, if we take that movie and we color code it, so each time point is represented by a different color image. Here you see the confocal image on the top, where because of the lower signal to noise it may not be clear when you see a calcium flash. At the bottom with the color coded image you see much more clearly what's going on. What I would point out is that the confocal image at the top, not only was it taken with half the frame rate, we needed to use 4 times the laser power here to get comparable movies. Now because it was a quicker pixel dwell, we used 4 times the laser power, but it means it was about 2.2 times the laser dose. So the laser dose being the total amount of light that the cell saw. So here you can kind of clearly see that we get better results with fast. And the group that did this then began to look at using fluo4 as a reactive oxygen species indicator. So what this means is, as you expose the sample to more light, it will react, it will create oxygen species which will lead to phototoxicity, and you can plot that in the intensities. If you do that on these cells, you see that if you use Airyscan fast, okay, there will eventually be reaction with the light and you will get some reactive oxygen created. If however you use the confocal, and in this case with 2.2 times the laser dose, you create oxygen, you create phototoxicity at 2.2 times the rate. So there's nothing magic here, it's simply the more laser power in a finer, more concentrated spot, you're going to introduce more toxicity. So there was a paper published purely exploiting or looking at this effect. Now, because the Airyscan is, particularly in fast mode, is such an amazing imaging system, you're going to find that everybody in the facility wants to use the system. So time can get limited. So time matters even if what you're doing is more routine imaging. So in this example I want to show a tiled example. On the left hand side you see a gallium arsenide PMT imaging. On the right hand side you see the same sample imaged with fast, and it's 4 times as quick. So if you've got 1 hour to get in, get on the system, get through as many slides or as big an area as possible, the fast will allow you to do that 4 times as quickly. And if I zoom in on this tiled acquisition, even though it's at 4 times the speed, you get better results. So it's simply better results more quickly. If I now come to a developmental biology example, this is a Z stack taken with Airyscan at the bottom, gallium arsenide on the top of a Drosophila embryo. In this case this was taken with a 20x 0.8 air lens, and the reason being so we could capture the whole field of view simultaneously at a very good sampling rate. This image is about 3,300 pixels in X and 1,400 pixels in Y. If you zoom in, you see that with Airyscan, even though this is taken with a 20x air lens, you get much better signal to noise and resolution still, and you can get that over time. So here we have the 3000 by 1,500 pixel image taken with 55 Z planes every 3 minutes for about 3.5 hours. And you can really, if you look around the movie, you can begin to see individual cell division and no bleaching. That's the power and speed that you get from fast. And because the system is so fast, it also means that if you couple that with, say, a Z piezo, so this is a fast focusing device, you can begin to think about doing Z stacks in the second or sub-second range. This is a multiphoton example taken with 920 nanometer excitation with 9 Z planes taken, but the 9 Z planes are taken over 18 microns and they're taken once a second. So in the top left we have a maximum intensity projection, and then the bottom left and in the orthogonal tilted movie here we see a depth coded projection. So cells which are flashing at the top of the stack are seen in blue, cells which are 18 microns deep into the stack are shown in red. And this really allowed the group to see interactions and responses in how cells lit up, just in a way that they weren't possible to see in 3D before. Now, when you're looking at super resolution in the form of Airyscan, and also the sensitivity it gives you, it also still, of course, comes back to speed. Here is a group or an image taken that was looking at a Arabidopsis root. Here we have the ER membrane with GFP shown in green, and in magenta we see the Golgi with RFP. The group here are particularly interested in the structure of the Golgi and how, if you zoom in, it looks donut shaped. The problem is, if you image with the gallium arsenide or in normal confocal, for them to get the signal to noise they need to slow down and average. So the image on the left is taken with one image every 2 seconds, whereas with the Airyscan they can get the signal to noise they need without killing the plant at 2 frames a second. So much quicker imaging using the Airyscan in this fast mode. If we zoom in and just look at the Golgi labeling, here we see really the kind of take-home message or the comparison between the 3 imaging modalities. You have LSM on the left with gallium arsenide, you have Airyscan on the right clearly showing the donut structure, and you have fast mode in the middle where you can still resolve the donut structure, but you do it at 4 times the frame rate. So it's really, you can choose exactly where you need to be for your application. So then finally, the last movie I'd like to show you today is a depth-coded projection again with 100 slices taken every 5 minutes for 2 hours, in this case of GFP in C. elegans. C. elegans is renowned for being, whilst a useful model organism, it can be a pain to image because they can be very photosensitive. And here we're able to do this for 2 hours on the fast with no bleaching, no toxicity, no change in development. So I hope I've made clear that the Airyscan really brings you the whole 3 corners of the triangle of confocal, signal to noise, resolution and speed, depending on how you choose to drive it. And the new fast add-on is going to open up new research possibilities within the realms of confocal. And the Airyscan itself is available as an upgrade to 710 and 780 systems, and in addition to 880 systems, the fast module I've mentioned at the later half of the talk is available on 880 systems. And with that, I will close my talk and open up for questions.
Thanks for the excellent presentation. We have a few questions from the audience. If anyone else has a question, please feel free to post it in the questions box that appears on the right of your screen. So the first question we have is, once you upgrade to the FAST method, can you still collect normal Airyscan images?
Okay, yes. Yeah, the fast upgrade is really just an additional functionality to Airyscan. Once it's there, you can switch between normal Airyscan and fast Airyscan in the software. You simply choose what you want to do in any given experiment. If you get really complex, you can use Experiment Designer to mix and match between them and do fast and normal Airyscan in the same experiment. But yeah, normally it's just a button in the software. Choose which method you want to use. Okay.
Okay, and so our next question is, can FAST work with the multiphoton?
Yes, yeah. So the calcium image near the end with the zebrafish stack, that was 1 stack per second. That was done with multiphoton, I think at 920 nanometer excitation. It's no different from using it in confocal mode. We still shape the excitation beam, in this case the infrared excitation, into a mini line to excite 4 pixels at the same time. And yeah, for the rest of it's the same as in confocal mode.
Okay. And then we have a question about the Drosophila movie, it looks like. Okay, so the Drosophila movie looks similar to data from your light sheet system. So how does the fast mode compare?
I must admit, I thought, I thought that it was kind of quite similar the first time I saw it. The Airyscan fast mode has better resolution. So if I kind of throw confocal in the mix as well, fast mode will have better resolution than confocal. Light sheet will have slightly worse resolution than confocal. So okay. Yeah, fast will give you the best results. And in fast mode, you're going to have better suppression of scattered light. On the other hand, fast is quite like light sheet in that you use parallel illumination to reduce the light going into it. But in fast, you do it by about a factor of 4, and you have better signal to noise. Light sheet is massively parallel. So it's very, very parallel, very good at long lifetime imaging. So I'd probably say they're all similar, but confocal you might image for a few minutes. With fast, you can image for a few hours, and with light sheet, you might image for a few days.
Oh, wow, okay. So that's quite a difference. And so then we have a question, are you planning on introducing the hybrid detectors into the LSM 880?
Okay, we already do. We use the hybrid detectors on the 880. We've got about 6 different detector technologies in the 880. Hybrid is one of them. So yeah, we've used hybrids since about 2009, I think. So on earlier generations as well, and we use them for FLIM imaging, so lifetime imaging. Anything where you scan very slowly, they can work quite well. For more routine imaging, we tend to get better results from gallium arsenide phosphide because they've got the same quantum efficiency, but they tend to give us fewer artifacts, better dynamic range. So they work not just with dim samples, but also with medium and bright samples.
Okay, and then then we've got a question about the signal to noise ratio. So why is the signal to noise ratio so much better with Airyscan?
Many reasons. The one is that you acquire a slightly bigger or light from a slightly bigger area than you would with one area unit. That effect, though, is quite minor because we tend to only collect about 1.2 area units. The main reason, so the big jump you get, is that you're condensing your light. So because you're improving the resolution, if you imagine you've got 10 photons in 4 pixels, and instead you end up with 40 photons in 1 pixel and nothing in the rest, that kind of condensing effect of the PSF gives you a much better signal to noise. You do get some improvement because you're averaging over the 32 detectors. So if one of the detectors, if you get this spurious noise you might get from heat or cosmic rays, that gets unmixed in the wash, and shot noise theory means you can pick out noise that shouldn't be there. And you do get an improvement from deconvolution. Now, you could do deconvolution on confocal, as I alluded to, but with Airyscan, you've got much more signal, so you can do that kind of nicely, without risking artifacts.
Okay, and then I've got a couple of questions from the audience about upgrading with the 880. So we have a question, so can you upgrade with the 880 Airyscan to fast module?
Yes, the 880 with if you've already got an 880 and Airyscan, you can upgrade to fast. It's a field upgrade with some hardware, some software changes. Speak to us. Okay.
And then we have some other questions about upgrading. So can you upgrade with do you need an 880 or can it work with the 800 system as well?
The fast is only available on the 880. You can get the Airyscan on the 800, but you need the 880 for the much more. The fast makes quite a lot of data quite quickly, so you need the top end electronics.
Okay, and then we have a question about more about the technical aspects. So does fast mode sacrifice resolution along the X, Y, and Z, or X, Y, and Z, depending on where you're from?
Okay, yes, compared to Airyscan, you roughly get an improvement of 1.5 over confocal, but Airyscan will be closer to 1.7 over confocal. But yes, and it is slightly better in X than Y. But yeah, all round with fast, you are better than confocal, and you get the signal to noise improvement.
So there was somebody else who asked a related question, and they're asking about, so the fast module Airyscan can work at quote unquote regular Airyscan mode, and they mean that you'll still get that 1.7x increase in resolution with the fast module.
Sure. You simply, we instead of doing the mini line excitation, we revert back to spot illumination, change the software. It's kind of one click in the software, and you're back to the normal Airyscan mode.
Okay. And let's see. I think we've got one more question, and it's about. Sorry, okay, we've got one more question that we can take, and they're asking if it's possible to take, let me see, sorry. Nope, they're asking about how thick can the samples be with the Airyscan?
It's really, it's always a how long is a piece of string question.
Right.
It's as thick as you can get on confocal. Okay. So if you're used to imaging it on confocal, you can image it on Airyscan. Similarly, if you can image it on multiphoton, you can image it on Airyscan. So, I've imaged some samples in viz mode where I've struggled to go beyond 50 microns. I've imaged other things where I've done 0.5 millimeter, and in multiphoton, it scales accordingly. If you're really pushing a deep scattering sample where you would see nothing in confocal, then you will begin to struggle with Airyscan, and eventually, you probably prefer to use multiphoton, but certainly deep. And what's really nice is you get the signal to noise improvement and the resolution improvement regardless of how deep you are. So it doesn't
that's really
degrade. Good. Yeah, it doesn't degrade like some of the other super resolution techniques.
Well, fantastic. That's really cool. So anyhow, that brings us to the end of the seminar. And if the audience wants to look in their chat window, you should have received several links to more information from ZEISS, as well as an email to contact ZEISS to get a quote or book on a hands-on demo. So thanks again, Chris, for a very illuminating presentation and a great discussion. And thanks also to our sponsor, ZEISS. And finally, thanks to you, the audience, for taking the time to attend and listen in. If you've enjoyed the seminar and would like to view the video recording of the session, please visit the seminars page on bitesizebio.com. It should be available within the next 24 hours. There, you can also see the other webinars we have lined up for you in Bitesize Bio's Webinar Festival. So until the next time, good luck in your research and goodbye from all of us at ZEISS and Bitesize Bio.